Hello, this is Josh Carter of Group 4, and we're here to present the solid-state visible and UV Prudinium yield laser system. Strap yourselves in because this is about to be a wild ride on the photonics train. So first, we're going to give a little outline of how we're going to present this engineering system to you. First, we got our project purpose overview, just a brief orientation around the motivation and objectives for this project. Then we have a design overview, which will be split into our 3 separate sections. First, an overall system integrated schematic. Then we'll go into our laser system, the theory and simulations of it, testing and troubleshooting, and then what remains to be done. From there, we'll go on to the power supply, hardware and software design, testing, troubleshooting, and then what remains to be done. Then we'll go into the user interface, the definition of it, an example of one, constraints, and its operation. From there, we'll see how the systems need to be integrated, maybe some problems that have arisen around that, project progress overall. Then we'll wrap it up, show you the action items of what remains to be done.
Hello, my name is Lady Moreno, and I'm going to be talking about the project motivations and objectives. This project is intended to help the photo in this processing group with their current UV laser. Our system will reduce the initial and maintenance costs of the required input power and the beam diameter. Our solid-state laser is more durable and efficient than the current UV laser in use. This project aims to be a balance between engineering and research, pushing forward the field of second harmonics in resonators.
UV lasers are commercially utilized in a variety of applications, but the only application that we're interested in for this project is holographic phase mask recording. That's exactly the purpose of the group at Creole that sponsors this project.
Hello, my name is Patrick. So our system has 6 subsystems. We have the user interface, which is an Android app that is connected via Bluetooth. We have the power supply unit created by Aaron. We have a PCB, which includes all of this logic and other stuff. We have a pump. We have a pre-cavity optics. We have laser cavity, and it has a cooling system for the crystal casing.
This next section is an overview and catalog of the engineering process involved with designing and building this laser system.
Our system has a laser diode that provides excitation for the gain crystal. The gain crystal has a side with an HR coating and with a curved mirror as an output coupler. An extending wave is created in the cavity. When it starts lasing, we will be lasing at around 640 nanometers, which will be converted into 320 with a second harmonic generation crystal.
Here's the photonics system layout and output specifications. It's depicted here, the optical and electrical characteristics that are necessary for this laser to function how we want it to. Here we have a pump power now of 3.91 watts, and we need a minimum output power of 10 milliwatts, so we don't need that much efficiency. The pre-cavity, as stated before, consists of a diode, half-wave plate, and an optical system to create an optimal spot size. The cavity itself has the high reflective mirror at 640 nanometer, coating the backside of the crystal, a nonlinear crystal, the BBO, a reflective Bragg grating as the output coupler, so we can achieve the line width of 0.1 depicted in the table next to me. To make sure that this cavity would be stable, we simulated the entire system in a system called Resonator. In Resonator, we were able to see the wavefront changes at each interface, and we figured out the target spot size for our optical system preceding our laser cavity. Here we see that the laser cavity itself needs to be 4.6 millimeters to have optimum stability. After knowing that we needed a minimum spot size of 62 micrometers, it was easy to take the lenses that we already had in the lab and figure out the distance between them necessary to create a fast focus system that gives us a spot size that is less than or equal to 62 micrometers. What we ended up with was about 61.8, so I'd say we got close.
The near crystal has two absorption axes. We are using a laser diode because the light coming out of it is already polarized. On top of that, we are using a halfway plate to match the polarization of the laser diode to the absorption axis of the crystal.
The cooling system for our crystal casing is a simple system. There's no too cold for this crystal before it breaks. There's only a too hot, and the optical qualities of the crystal will change before then. Our cooling system consists of a thermoelectric cooler and a heat.
In the testing and troubleshooting of this laser system, it has gone through many evolutions and iterations. The system itself is currently in its 30th iteration and is much different from the aforementioned system. This is because the first diode that we were using actually degraded further as we used it more. So to give an example, the diode needs to be around 444 nanometers. It began already at 450 nanometers, but the target wavelength is well within its full width half max. So we figured it should be fine. The diode actually was degrading at a really fast rate, and its cooling system wasn't effective enough to keep it from migrating away from the center wavelength that it's advertised at. This caused a variety of issues. On top of that, we had other issues like, if you can look down here at this mirror, the golden mirror that is now burned and broken, that's because gold has an absorption line at 450 nanometers. Another issue we saw with our cavity, or believed that we had, was that perhaps the beam profile coming out of the diode was too nasty to actually achieve stability within the cavity. Perhaps the problem was that the mode itself could not form a stable standing wave. So to fix this, we used an optical fiber and coupled our light from our pump laser into it. And so we would get a Gaussian output at the end. We know a Gaussian output is always stable within a cavity. The problem with this, however, is that we only got 83% coupling efficiency, which is actually very good for a fiber optic. The problem with that, though, is that fiber optics naturally are not polarization conserving. And so we had to use also, in conjunction with the fiber optic, a polarization cube. This introduces another loss of 50% power after the 17% that is lost through the fiber. This was unacceptable and actually would leave us with too little power to achieve lasing.
After realizing all the issues the other laser had, we decided as a group to shift to another laser. These new lasers allowed us to control the current and temperature, which let us tune it to a desired wavelength, in our case 443 nanometers. Also, the beam quality is much better than the previous laser. As well as we have more power on the system to pump the crystal. Thanks to this new diode, the power absorption is about 83% of 3.9 watts. Due to this high power, we're gonna need the TAC so the crystal doesn't get damaged. After building the system 30 times, we are very close to lasing once we implement the TAC. After rebuilding the cavity 30 times, we are very optimistic on getting lasing in about 2 weeks. The next steps are fixing the alignment and implementing the TAC.
The electrical layout as shown in this slide shows how every module are connected and working together to come up with a power supply box. Here we can see that a 12 power supply made specifically with a full bridge rectifier is built to output 1 amp. Every Arduino chip extracts a certain amount of current from the power supply. Since every Arduino Uno current rating is 200 milliamps minimum and 400 milliamps maximum, then they are going to get that much current to power up the chips and program the other modules. For the electrical layout, since we cannot output large amount of current and voltage, a relay is implemented at the end of the pulse width modulation to increase the power to 24 watts maximum, 2 amps. Every Arduino outputs 5 voltage for the display to be connected and so on. And finally, a 12 DC voltage fan is connected to the power supply, connected to the same relay with PWM and fan modules turn on and off. Here we discuss the requirements and specifications for the most important elements in our circuits. Commenting over what I said on previous slide, the voltage supply is going to give 12 voltage DC to fan and laser input. And adding to this, there's the ASP8266 using memory to upload the image to the TFT display. Lastly, the touch sensor, most important information not mentioned before, is that it has a debouncing time of 1.5 seconds for it to work properly. Power supply schematic give the overview of how simple and at the same time well compacted the powering of each module really is. PCB building tend to be obnoxious when routing every single component. That is why in this part we used the rat nest tool and utilized a 2-layer board feature so that every part can communicate with each other. While building the reading display of current, power, and voltage, we try to simplify the process, at the same time execute a different way of creating the PCB, 1-layer rat nest, which just connects the ground to the bottom layer and make use of only 1 layer in the PCB frame. As done in previous slides, a PCB is made by using rat nest feature in Eagle to simplify a little bit the process of routing, but this time we wanted to implement VS to see how this feature will affect the PCB layout. As thought, with the VS tool, the PCB looks more professional, well organized, and simplified overall. This module is the most important PCB layout in our logic board. It outputs a PWM signal to the laser. We didn't apply the relay and boost module in this schematic since we still don't have the right calculation and or components to simplify or supply the power to every module. This module is the most important PCB layout in our. Since we already bought the ESP8266 module, we prefer to just solder the board to our custom-made PCB and save some building time. TFT OLED 128 by 64 need a memory, and that is exactly why an ESP Arduino module was used. Eagle didn't let me open bom.csv file, but below are the images of each file. Power supply bump was the first one to come up. Every single component used to build this schematic is attached below. The bill of material doesn't have the prices since we haven't added the products into each element. Since we don't have the components attached to each element, we don't have the Gerber file for the PCB to be manufactured. This is the laser PWM, pulse width modulation. Here we have the mini oscilloscope, BOM. Since every module is powered by Arduino Uno R3 chipset, the bill of material are very similar. For the temperature control, some components are missing since we already own a 12 DC fan and DHT11 temperature sensor. Since the ESP8266 is a very small synthesized module, The bill of material is very simple and small too. Here we have the bill of material of the reading display INA 219. Here are some of the issues we have faced so far. PCB delivered not on time, parts not available because of shortage, calculation errors, having to redo PCBs, not enough current delivered to AT Mega 328P and ESP 8266 chips, and having finally to build more complex amplifier.
Although our new diode is more robust and better than the last diode in every conceivable way, the one way that it's not better is it's a lot harder to integrate with. So this change in input and output for the cables that connect this diode to its power supply makes the power supply that our electrical engineer has been working on obsolete to this system. This is why this decision was so hard to make and why it took 30 iterations to go ahead and go to this more robust diode. We want the laser system to work, but we also want it to work with the intended power supply. We're not sure how to solve this problem yet, but we are still troubleshooting.
Our user interface is an Android-based application designed for smartphone use. We chose to use this type of user interface for two reasons. One, graphical user interfaces, or GUIs, are easy and simple for all users to use, not just professionals. Secondly, there is a perception that GUIs are more professional appearing than command line interfaces or analog banana interfaces. We all know perception is key. As I mentioned before, this is an Android-based app for use on a smartphone. More specifically, it's an Android-based app for use on a smartphone, programmed with React Native framework for use with the HC05 Bluetooth module. Bluetooth provides enough security such that there is very minimal risk of hacking into the system. But the rewards of using it is great because there's no wires. The user interface will have the following features. The user will obviously be able to turn on the laser from the app, but additionally, he or she will be able to switch between continuous wave mode and Q switch mode from the app. Furthermore, they will be able to monitor the temperature of the crystal casing and the power consumption of the laser directly from the app.
All things considered, our project stands at about 52% completion. We're on track, and the only issue that is especially glaring is the integration of the power control to the laser system. This is something we're still actively trying to solve and trying to come up with a solution that can work for everyone, where our electrical engineer doesn't get put in a situation where he has to redesign everything that he's done because of the degradation of a piece that we had already. We don't have time to create a really robust solution to this, so we are open to other people's input as to what we should do with this. Thank you for listening to our presentation, and this has been Group 4. You have a wonderful day.